Hi, my name is Michelle Trott, Scientific Content Manager at Izon Science. In the last video, I talked about why it's important to measure lipid nanoparticles, or LNPs, accurately, why it matters in the context of nanomedicine production and regulations, and a few different approaches to comparing particle size. Today, we're going to delve into a comparison of two methods for measuring LNPs. For many years, the go-to method for measuring these intricate, cleverly designed lipid nanoparticles is one with some pretty major limitations. That method is dynamic light scattering, or DLS. While DLS is a quick and easy-to-use method that gives you an insight into the intensity of light scattered by particles in solution, measuring light scattering is not the same thing as measuring particle size or concentration directly. However, it's what most people seem to be doing. But is that really a solid rationale for choosing an analytical technique? Let's delve into some data. Here we have external data illustrating the size distribution of mRNA-loaded LNPs, as assessed by DLS. On the surface, it appears to showcase a fairly normal distribution with a low polydispersity index, indicating a seemingly clean dataset. This ultra-smooth appearance is a characteristic trait of DLS, as it is an ensemble method, meaning it doesn't provide independent data points for each individual particle in your sample. Consequently, the output is an overly smooth curve, giving the data a polished, almost artificial look. But does this reflect the reality of the sample? The downside of this low-resolution approach is that certain nuances and details inherent to the sample can be missed, resulting in a loss of what could be highly valuable information. There is another way. Tunable resistive pulse sensing, or TRPS, is a technique with a much higher resolution than DLS. TRPS is a single particle measurement method with an exceptional ability to measure particles to a high degree of resolution. To get a better understanding of how it works, make sure you check out our video titled, "What is Tunable Resistive Pulse Sensing?" The precision and accuracy of TRPS surpasses commonly used light scattering methods that only provide bulk estimates. Let's compare that DLS data with TRPS measurements generated in-house using the same mRNA-loaded LNPs. You'll immediately notice that TRPS can provide much more nuanced information. First, we identified a non-normal distribution, making mode size the most appropriate to report. TRPS showed superior resolution, pinpointing that the mRNA-loaded LNPs were markedly smaller in size than what was indicated by DLS. Here, the size discrepancy was 25 nanometers. Next, it's quite apparent that there actually is some polydispersity. This is reflected in a slightly higher polydispersity index of about 0.09, as compared to the 0.08 reported by DLS. While this might seem like a small difference based on this measure alone, TRPS facilitates a much more thorough comparison of samples. This allows for the detection of even minor yet meaningful differences in size. In this case, TRPS was able to discern that the mRNA-loaded LNPs were smaller in size than the empty LNPs. Not only that, the empty LNPs had a lower concentration. With DLS, a size difference of approximately 3:1 is required to show peak resolution. In other words, if the size of one particle is twice that of another, DLS wouldn't be able to detect a difference. In stark contrast, TRPS offers significantly greater sensitivity. With TRPS, if the diameter of the particle doubles, it results in an 8-fold increase in resistive pulse magnitude. This makes TRPS a far more refined tool for detecting variations in particle size. Here it's evident that TRPS can effectively identify an increase in the size of mRNA-loaded LNPs following freeze-thaw induced aggregation. Although we intentionally induced this aggregation, you might have aggregation resulting from a change in your formulation or manufacturing process, storage or transport. This underscores the importance of having a highly sensitive and accurate particle measurement method when analysing LNPs. Size and concentration is crucial for optimising your formulation in the first place, validating processes and quality control down the line. That measurement can only be conducted with sufficient resolution using TRPS. But don't just take our word for it. In the development of a therapeutic against SARS-CoV-2, TRPS was used to measure the size distribution of lipid nanoparticles loaded with a small interfering RNA. From this analysis, the researchers were able to calculate a polydispersity index of 0.16 and identify a mean size of 80 nanometers. This showcases the real-world application and effectiveness of TRPS in LNP analysis. Although TRPS measurements require more time and skill, they offer precise and detailed information on LNP size, concentration, and particle size distribution. With TRPS, you can also measure zeta potential, which is another key capability in the field of nanomedicine, but we'll save that for another time. With its ability to detect small differences in particle size and produce precise measurements, TRPS has a lot to offer in the nanomedicine field. Izon's latest TRPS instrument, the Exoid, is capable of providing measurements for size bands of nanoparticles ranging from 40 nanometers to 11.3 micrometers. By selecting a nanopore that is appropriate for your sample, you can capture a broad range of particle sizes. For example, the nanopore called the NP150 allows for size and concentration measurement of particles ranging from 70 nanometers to 420 nanometers. To learn more about how the Exoid can boost your LNP development process and quality control, reach out to us today through our website at izon.com. Thanks for watching.